And share my screen then. All right, so thank you very much for the invitation to speak here. I'm really excited for the discussion and to see what you guys think of these ideas. So I'm going to be talking about explanatory definitions and explanation in mathematical practice. So these topics are coming from two different papers of mine, the synthase one that Henrik mentioned, and then another one called Mathematical Explanation in Practice. And basically, I just want to try to introduce today my idea of how we might think definitions are explanatory and why it might be valuable to do so, or why I think it is valuable to do so. Okay, so again, my goal is to introduce the notion of explanatory definition as I conceive of it, and to consider the significance for mathematical practice. To do this, kind of a brief outline, I'm going to first start by unpacking what I call kind of a traditional approach to explanation and point out some ways that it seems to be lacking when we think about explanation in mathematics. I'm then going to consider the role that definitions play in mathematics and try to propose a characterization of what it means for a definition to be explanatory. I'll then look at two different examples that I think highlight some of the features of explanatory definitions, and then I'll briefly comment on the value and significance of explanatory definitions for mathematical practice more generally. So I'm kind of going to give somewhat of a brief overview of each of these points because I want to kind of leave a lot of room open for discussion. So definitely, if you have questions as I'm going through or want more detail in the discussion, definitely feel free to ask when we get to that discussion time. Okay, so to start off with kind of what I'm thinking of as the traditional approach to explanation is the approach in terms of why questions. So in philosophy, when we think about explanations, we're often thinking about answers to why questions. Now, certainly this isn't completely representative of everything that's been said about explanation in the philosophical literature, but I think that oftentimes we are thinking about why questions and how we answer them, and that's how we kind of intuitively seem to be thinking about explanation. So if we apply this in the context of mathematics, then when we are looking for an explanation, we're asking, why is this theorem true? And we're looking for a proof that answers that why question, that tells us why that theorem is true. So an explanatory proof will be one that clarifies not only that the theorem holds, but also why it holds. And similarly to how this talk of why questions has been kind of central to the talk of explanation in philosophy more generally, I think this talk of explanatory proof has been central to the talk of explanation in the context of mathematics. So many accounts of mathematical explanation have thus far centered around developing an account of explanatory proof. Okay, so just to briefly overview some of the literature, some well-known accounts of mathematical explanation that you may be familiar with are those of Mark Steiner, Phil Kitcher, and Mark Lang. So Mark Steiner puts forward an account of explanatory proof in terms of characterizing properties, where roughly the proof will be explanatory if it exploits some characterizing property that's appealed to in the statement of the theorem. Kitcher gives an account of explanation in terms of unification. So if you have a unified argument form that your proof is kind of an instance of, then you'll have an explanatory proof. And Mark Lang gives an account of explanatory proof in terms of salience. So a proof is going to be explanatory if it makes use of a property that's salient in the statement of the theorem, or salient of the subject of the theorem. So those are kind of brief overviews, but I wanted to mention them because I think each of them really centrally is focused on this talk of explanatory proof. So both Steiner and Lang talk about the fact that it seems like there are other forms of explanation in mathematics, but the bulk of the work that they put forward in terms of giving account of explanation is focused on explanatory proof. And so these are kind of thought to be kind of maybe this three classic views of mathematical explanation in the philosophical literature, and each of them really does seem to centrally focus on explanatory proof. So what you might wonder is whether or not we're losing any kind of insight into what mathematical explanation is when we really restrict our lens to explanatory proof. So I think it's quite clear from mathematical practice that when you're doing mathematics, both as a researcher and as just a student or a learner, you aren't just restricted to talking about theorems and proofs. You're not just putting forward a theorem and proving it and doing that over and over again, but instead there's other aspects of mathematical practice that come into play, right? The role that definitions play, as I'll talk about in this talk, seems to be really significant. Finding examples that help to illustrate what you're talking about and what properties you're interested in is really important. Looking for counterexamples is really important. And so it seems like thinking about mathematical practice simply in terms of theorems and proofs is an oversimplification. And similarly, I think thinking about mathematical explanation only in terms of theorems and proofs is also going to be an oversimplification. And so that's kind of where I'm motivated to look for other forms of explanation in mathematics. And that's why I first kind of wanted to think about mathematical explanation in the form of definitions. Okay. So that being said, the main question I wanted to raise was, can definitions be explanatory? And what exactly would that look like? So I think to answer this question, we first have to think about what explanation is meant to achieve and the role that explanation and definitions play in mathematical practice. So when we think about mathematical explanation, again, I think it's an oversimplification to think that we're just trying to figure out why theorems are true. It seems like instead what we're trying to do is get a grasp of the mathematics in a meaningful way. So we're trying to move past this idea that mathematics can be understood as just spitting out values of like true or false, and instead we're really trying to understand and grasp what's going on. So essentially, I think that mathematical explanation is really intimately connected to understanding, and that in order to make sense of mathematical explanation and understand all of its complexities, we need to think about what contributes to our understanding of mathematics and how explanations contribute to our understanding. So I guess I got a little ahead of myself, but yeah, so this point kind of unpacks that idea. So I think, again, we need to be looking at what contributes to our understanding and whether or not whatever is contributing to our understanding constitutes an explanation. All right, so the second thing that I think we need to consider before we can jump into an account of explanatory definitions is what role definitions are playing in mathematics. And I want to consider both the kind of educational role of definitions and also the role that definitions play from a research perspective. So I think a brief gloss of the role that definitions play can be stated as capturing conceptual information in a way that's really meant to provide an introduction and a representative characterization of the notion. So from an educational point of view, when we are introduced to a definition, that's really our first introduction to that mathematical concept. So when you're being introduced to the definition of function, that's really your introduction to the formal concept of what a mathematical function is. You might have seen some functions before, but it's giving you kind of the representative characterization of what a function is, and it's introducing you to how you kind of should continue to think about functions and what unifies all of these different kind of examples of functions that you might have previously seen. So I think that definitions play a crucial role in an educational perspective because they're that first kind of starting point that you have to wrap your head around a mathematical concept, and anything that you're going to conclude about that mathematical concept moving forward is going to be in some ways derivative of that definition. And derivative there being like a loose sense, not, yeah, a loose sense. And then from a research perspective, I think that definitions are developed to capture mathematical observations that constitute conceptual significance. So to kind of unpack that a bit more, I just wanted to kind of include that in the process of defining new concepts in mathematics, when you're kind of exploring new areas and actually partaking in research, when you're trying to present a definition, what you're trying to do is use your past observation of mathematical phenomena to kind of put forward, again, this representative characterization that you can now work with and use to study whatever kind of phenomena you observed. So essentially, you're trying to put that observed phenomena into some kind of conceptual formation and understand all of its complexities. We need to think about what contributes to our understanding of mathematics and how explanations contribute to our understanding. So I guess I got a little ahead of myself, but yeah, so this point kind of unpacks that idea. So I think, again, we need to be looking at what contributes to our understanding and whether or not whatever is contributing to our understanding constitutes an explanation. All right, so the second thing that I think we need to consider before we can jump into an account of explanatory definitions is what role definitions are playing in mathematics. And I want to consider both the kind of educational role of definitions and also the role that definitions play from a research perspective. So I think a brief gloss of the role that definitions play can be stated as capturing conceptual information in a way that's really meant to provide an introduction and a representative characterization of the notion. So from an educational point of view, when we are introduced to a definition, that's really our first introduction to that mathematical concept. So when you're being introduced to the definition of function, that's really your introduction to the formal concept of what a mathematical function is. You might have seen some functions before, but it's giving you kind of the representative characterization of what a function is, and it's introducing you to how you kind of should continue to think about functions and what unifies all of these different kind of examples of functions that you might have previously seen. So I think that definitions play a crucial role in an educational perspective because they're that first kind of starting point that you have to wrap your head around a mathematical concept, and anything that you're going to conclude about that mathematical concept moving forward is going to be in some ways derivative of that definition. And derivative there being like a loose sense, not, yeah, a loose sense. And then from a research perspective, I think that definitions are developed to capture mathematical observations that constitute conceptual significance. So to kind of unpack that a bit more, I just wanted to kind of include that in the process of defining new concepts in mathematics, when you're kind of exploring new areas and actually partaking in research, when you're trying to present a definition, what you're trying to do is use your past observation of mathematical phenomena to kind of put forward, again, this representative characterization that you can now work with and use to study whatever kind of phenomena you observed. So essentially, you're trying to put that observed phenomena into some kind of conceptual form so that you can move forward and further study it. So essentially, both of these different perspectives are really focused on giving us a way to interact with this concept and, again, wrap our head around this concept so that we can move forward and make mathematical progress. And so definitions play, I think, a really important role, because when you have kind of a good definition, you're going to be in a good position to move forward mathematically and to raise interesting research questions, to answer research questions that already exist, and just further your understanding of the fields that you're studying. Okay. Yeah. So with that being said, I now want to propose or present my characterization of what explanatory definitions are. So what I mean by explanatory definition is a definition that answers what I call the what's going on here question. So I kind of mentioned in the beginning that traditionally explanation is understood in terms of why questions. And I think that this kind of naturally leads to the explanatory proof picture of mathematical explanation. And so I think alternatively, so that we can get a more complete characterization of mathematical explanation, we should raise this question, what's going on here? And when we ask this what's going on here question, what we're trying to do is we're trying to really, again, wrap our heads around or grasp that mathematical concept and also understand how it's situated in the mathematical setting. So we don't want to just be able to parse what the definition says and be able to make kind of logical sense of it, but we want to get a picture of how that definition actually fits into the field of mathematics that it lives in and how it maybe even relates to other areas of mathematics. And we want to get some kind of answer to this what's going on here question. And I think this question is a better one to use when we're thinking about explanation, because I think, to be honest, it's one that comes up more than straightforward why questions in mathematical practice. So it's often the case that when you're doing mathematics, you may be a bit confused or a bit lost about what exactly is happening. And I think it's natural to ask, well, what's going on here? Let me sort this out. Let's figure things out. And when you're figuring those things out, what you're ultimately doing is looking for an explanation to explain whatever kind of had confused you or whatever seemed surprising. And so I think it's kind of a more natural way of capturing how explanation arises when you're actually partaking in mathematical practice. Okay, so a consequence of answering this what's going on here question is that I think we end up getting more familiarity with the concept. So again, we're better able to grasp it and wrap our heads around it. And that in turn increases our understanding of that concept and the area of mathematics in which it lives. All right. So I wanted to mention, this kind of came up a little while ago, but this way of explanation and the way that I'm thinking of this what's going on here question is meant to be similar to a functional account of explanation where, again, I'm thinking of explanation as being intimately related to understanding. And so I think that explanations are going to be kind of one of the main ways in which we gain mathematical understanding. All right. So I now want to get into some kind of more concrete examples to unpack the sense in which definitions can be explanatory. But before doing that, it's worth pointing out that this question of explanatory definitions seems to kind of naturally arise when we think about the fact that in mathematics, there's many different ways to define the same concept. So it's a common phenomena that when you're studying mathematics, you'll come across a new definition of a concept that you've already seen defined. And so William Thurston, in his paper on proof and progress in mathematics, raises this point kind of famously and talks about how you could characterize the notion of the derivative of a function in a bunch of different ways. So he explicitly lists out 7 different definitions that you could give of the derivative, but he suggests that there may be up to as many as 37 definitions. And he really doesn't put a cap on how many definitions you might be able to give of what the derivative is. And this whole, or the point of this discussion is just to say that there's lots of different perspectives that you can have on the same mathematical concept. There's lots of different definitions that you could give of the same mathematical concept. And I think when we're thinking about explanatory definitions, this is important to note because it's kind of naturally giving rise to this question of how do different definitions compare to one another? When is a definition the right one? And what kind of is the epistemic advantage of using one definition over another in a specific context? So I'm kind of going to use Thurston's example of the derivative as kind of my first example or as my starting point. And I want to look at 2 different ways that you might define the notion of derivative. So one definition, which is one that Thurston gives, is that the derivative of a polynomial function is given by the rule that the derivative of a times x to the n is n times a times x to the n minus 1. So just the usual algorithm for calculating the derivative of polynomials, together with the idea that the derivative of a sum is the sum of the derivatives. So you might raise the question of whether or not this definition even is kind of a genuine definition, but insofar as it seems to give a representative characterization of how you get the derivative of a polynomial function from that function itself, it seems like it could at least be a contender for a definition when we understand definition broadly. The second definition of derivative that I want to talk about is the definition in terms of the limit of the slopes of the secant lines. So it says that the derivative of a function at a point is the limit of the slope of the secant lines approaching the tangent line at that point. So that means that we can represent the derivative of a function at a point A with this nice little equation involving limits. Okay, so now if we want to look at these 2 explanations and consider, these 2 definitions and consider whether or not they're explanatory, we have to think about what exactly we're gaining from each of these definitions. So what the first definition gives us is an algorithmic method for computing the derivatives of polynomials, but it doesn't really provide any insight into what the derivative is as a concept, right? So if you already have a good understanding of the concept of what the derivative is, then you might be able to see how that concept is playing a role in that algorithm. But if your first introduction to the notion of derivative is just that simple algorithm, then you're not really going to have any idea of what the derivative really represents or what it is conceptually or why it's conceptually significant. And so it seems like this first definition is lacking in its epistemic contribution. So again, it's telling us how to compute the derivative, but it doesn't really give us any grasp of the actual concept of derivative. And so I think for this reason, it doesn't seem to be an explanatory definition. It isn't giving us this way of grasping the concept that we need in order to have an explanatory definition. The second definition, I think, does a better job of giving us an understanding, and I think it does a good enough job to count as an explanatory definition. So the second definition gives us insight into what the concept of the derivative is. It tells us kind of a bit about where that algorithm is coming from. It tells us that essentially the derivative just is the slope of the tangent line. And so we get, and even more than telling us that the derivative is the slope of the tangent line, it also tells us exactly what the slope of the tangent line is, right? The slope of the tangent line is just the limit of the slopes of the secant lines. And so we get a much better picture of what's actually happening and what the derivative actually is tracking and what it represents. And I think that this is even kind of further emphasized when we look at a diagrammatic representation of taking the derivative with this definition. So we can look at, if we're looking for the derivative of this parabola at the point 2, 1, then we can see that we can just take a bunch of secant lines, and as we get closer and closer to the point that we care about, we're getting closer and closer to the slopes of the tangent lines. And so we get a much better kind of idea of what the derivative is actually representing and what the concept of derivative is really tracking. Okay, so for this reason, I think that we can say that the second definition does give us an explanation of the concept of derivative, whereas the first one failed to. All right, so from this example, we see that when we have an explanatory definition, we get this epistemic contribution that is just a better understanding of the concept being defined. So again, you can be really great at applying the algorithm that's given in definition 1 without having any kind of understanding or even recognition of what the derivative as a concept actually captures. And so again, I just want to highlight that when I'm thinking of explanatory definitions, I'm thinking about what the epistemic contribution is. And to be explanatory, a definition has to give us some understanding and insight into the concept that's being defined. So now I want to kind of highlight some more specific properties of explanatory definitions as I'm understanding them. And to do that, I want to kind of walk through another example. So the next example I want to think about is the definition of defining circle. And kind of similarly to the notion of derivative, the concept of circles seems to have a lot of different ways of being defined. So we can give the first definition that I give here, which says that a circle is the set of all points in the real plane that are the same distance or equidistant from a given point. So perhaps more concisely, a circle is a set of all points equidistant from its center. Okay. The second definition that we can give of circles is that they are the set of points in the real plane satisfying the equation x squared plus y squared equals r squared for some non-negative real number r. And the last definition that I give here is a topological definition where say that a circle is a topological space homeomorphic to the quotient space given by the unit interval with a standard topology under the equivalence relation that identifies 0 and 1 and identifies every other point with itself. So essentially definition 3 is just telling us that a circle is anything that's homeomorphic to the interval under this, the unit interval under this equivalence relation. So all three of these different definitions are meant to capture the concept of what a circle is, but they do so in different ways. And I think when we look more closely at the different ways that they do this, we get a better understanding of the value of explanatory definitions and what exactly explanatory definitions kind of bring to understanding and thinking about mathematics. Okay, so it's first worth pointing out that the first two definitions are logically equivalent. So let me go back really quick. So we can get from definition 1 to definition 2 and from definition 2 to definition 1. And essentially they're saying the same things, but in the sense that they're logically equivalent, but I think it's important to note that they're saying them in different contexts. So when we analyze definition 1, we see that it's characterizing or defining the circle in the context of the real plane equipped with the usual metric. So we're talking about the set of all points equidistant from the center. So we're implicitly appealing to the usual metric on the real plane. And so this definition gives us an understanding of circles in the context of metric spaces, and in particular in the context of the real plane as a metric space. So this definition, I think, formalizes our intuitions about circles in a way that introduces a mathematical understanding by highlighting the property that all points on a circle are equidistant from the center. So it's certainly the case that if you never do any mathematics, you still will come across circles and can understand maybe intuitively this idea that a circle has this property where all the points are equidistant from the center, and you may be able to kind of just intuitively capture that sense of what a circle is. But what this definition does is it gives us a formal way of capturing that intuition. So we're not just saying that circles seem to have this property where all the points are the same distance from the center. Well, I guess we are just saying that, but we're saying it in a way that's more mathematically sophisticated and that gives us more kind of mathematical machinery to think about these circles and understand how they fit into the context of the real plane and how they relate to other geometric shapes that we consider in the real plane. And ultimately, I think it just gives us this better understanding of the mathematical properties of what a circle is. So I think that this does constitute an explanatory definition in that it explains to us the mathematical property that seems to be representative of what circles are. So I think this is an explanatory definition. But when we compare it to definition 2, I think that we start to see some of the complexity that arises when we think about explanatory definitions. So let's first look at definition 2 and determine whether or not it's explanatory. So definition 2 is the one that characterizes a circle in terms of the equation x squared plus y squared equals r squared. And so it gives a characterization in the context of algebraic geometry. And this is a perspective that is different from the first definition. So again, definition 1 and definition 2 are logically equivalent, but they give us different perspectives on the circle because of the way in which they're stated. So this definition doesn't have any implicit appeal to, or explicit or implicit appeal to the usual metric on the real plane. And instead, it's giving us a algebraic characterization of what circles are. And so it really belongs in the realm of algebraic geometry, and it gives us this new way of thinking about circles. And when we think about this definition in the context of algebraic geometry, I think we again see that it introduces a level of understanding that the first definition didn't give us, and that we don't have just kind of intuitively from our observations of circles or our intuitions about circles. And so in particular, this definition gives us a clear way of comparing circles to other geometric objects that can be characterized in algebraic terms. So for instance, if we look at the characterization of ellipses in algebraic geometry, we have an equation that's really similar to the equation for circles, and the similarities, and importantly, the differences between these two equations can allow us to better understand this relationship between circles and ellipses. And so ellipses, the equation for ellipses is roughly x squared over a plus y squared over b equals r squared. And so when a and b are equal, you'll have a circle. And so we see that some ellipses are going to be circles, but not all circles are going to be ellipses. And that's something that we can immediately see when we compare these characterizations as they're given in the context of algebraic geometry. And so I think because of facts like these and because of the way that the characterization that definition 2 gives can be compared to other mathematical definitions and characterizations, we do get a better grasp of what circles are in the context of algebraic geometry from this definition. So I think similarly to the first definition, this second definition is explanatory because it is increasing our understanding and our ability to grasp what circles are, but it's doing so in a different way. And so from the comparison of these first two definitions, I think we can start to see some more detail about how the notion of explanatory definition can be unpacked and how it kind of arises in the context of mathematical practice. And in particular, I think we can kind of take two main points about the nature of explanatory definitions from this comparison of definition 1 and definition 2. And the first of these points is that the context of a definition matters when we're determining whether or not the definition is explanatory. So a big difference between definition 1 and definition 2 was, again, the context in which those definitions lived. So if you were trying to understand the real plane as a metric space and its properties, then giving definition 2, the one that is algebraically geometric. I don't know how to turn algebraic geometry into an adjective, but if you were trying to study the real plane as a metric space and I gave you the definition in terms of algebraic geometry, then it wouldn't be as helpful in you grasping how circles fit into that real plane as the first definition would be. And so when you're looking for whether or not a definition is explanatory, you have to look at the context in which you're dealing with, the context that you're dealing with and what exactly you're trying to achieve bigger picture. So again, if you take a definition that could be explanatory in some contexts and apply it in a context where it doesn't kind of naturally fit in, then it's going to lose its explanatoriness in that context. So you have to kind of be fair to the definition and consider it in its own context to understand whether or not it's explanatory. And this also is kind of useful to make note of when we're thinking about, in particular, the pedagogical role of definitions. So if you are presenting the definition from algebraic geometry to a class that isn't equipped to kind of understand the methodologies of algebraic geometry or to make use of kind of the explanatory features of that definition, then the definition is not going to play an explanatory role for them. So again, you have to think about the context of the definition, both in terms of where the definition kind of lives within mathematics and how you're trying to apply the definition to make kind of epistemic progress. Okay, so the second point that I think we can, that we gain from this comparison between definition 1 and definition 2 is that explanatoriness of definitions is a matter of degree. So, so we saw that, well, or at least I claim that both definition 1 and definition 2 are explanatory. But I think the way to understand how these definitions relate to each other is in terms of, is one more explanatory than the other? And I think that in this case, you could make a case that the second definition is more explanatory than the first, because when we think about the level of understanding that we're getting from the definitions, I think we get an understanding that's more mathematically sophisticated from the second definition than from the first. And so in that sense, the second definition is more explanatory than the first definition. And I think that it's important to recognize that explanatory definitions do come in different degrees, because I think this helps to make sense of why new definitions arise and how mathematics progresses. So it's certainly the case that you could give a definition of something to kind of a student who just wasn't equipped to appreciate that definition. And so that definition might be explanatory, but that student just won't recognize that. And it's not a fault of the definition or even a fault of the student. It's just a result of the relevant background knowledge, and in this case, a lack of that background knowledge to appreciate kind of the explanatoriness of the definition. So a definition that's more explanatory may also be less accessible mathematically. So in other words, you just need more mathematical background to appreciate that definition. And again, I think that it's important to recognize that the explanatoriness of definitions is a matter of degree, because I think it's important to understand how exactly explanatoriness is, how exactly our reception of definitions is related to our background knowledge, and how the epistemic potential of a definition isn't kind of determined by our background knowledge. If that makes sense. Okay, so let's briefly look at the third definition of circle that I gave, which perhaps is a bit more controversial. So I say that it perhaps is a bit more controversial because, unlike definition 1 and definition 2, definition 3 is not logically equivalent to the first two. So definition 3 again tells us that a circle is going to be a topological space that's homeomorphic to the unit interval under this equivalence relation, where essentially we just identify the two ends so that we get a closed loop, and a circle is going to be anything that's homeomorphic to that closed loop. And so what this means is that a lot of things that don't count as a circle in a metric space are going to count as a circle in a topological space. And so again, we don't have logical equivalence, but I think that definition 3 is still trying to capture the concept of circle. It's just doing so from a different perspective. So when we look at mathematics or mathematical objects from a topological perspective, we don't necessarily care about the same things that we care about in other contexts. And that's why we have this definition of circle that is much more broad and that isn't logically equivalent to the other two definitions. So, yeah. And I think, again, insofar as this definition is giving us an understanding of how we're thinking about circles from a topological point of view, so in particular as anything that's homeomorphic to a closed loop, we get a better understanding of what circles are topologically. And so I think, again, we're getting a more sophisticated understanding of what circles are, and we're getting one that I think gives us enough of a grasp of the concept of circle to constitute an explanatory definition. So again, I think this is another explanatory definition of circle, but I think that it's a different degree of explanation. So again, the topological concepts that are appealed to in this definition are much more inaccessible than the first two definitions were. And this just essentially means that the definition is itself more mathematically sophisticated, but despite that mathematical sophistication, we're still getting an understanding of what a circle is topologically. And so I think it still meets the criteria of being an explanatory definition. Yeah. And so I wanted to bring up this last example to kind of show, again, that the context really matters. So if you gave this definition in an algebra class where you're just talking about the real plane and how to plot points and things like that, then it would be a horrible idea, right? It would be a definition that wouldn't provide any kind of explanation to the students, again, because the students aren't equipped with the background knowledge to appreciate this definition. But when you apply this definition in the right context, namely in the context of topology, then I think you do get an appreciation and a better grasp of what a circle is topologically, and that's what makes the definition explanatory. Okay, so if we briefly summarize this comparison, so the topological definition certainly introduces the highest degree of mathematical sophistication. And so I think it allows for the most significant development of mathematical understanding. So when you're introduced to that definition and when you kind of conceptualize it successfully, that's when you're going to have kind of the highest level of mathematical understanding. And so this makes it more explanatory than the other two definitions. Oh, so I contradicted myself in the second point. So definition 1 and definition 2, I think, are both explanatory. So this is something that I go back and forth on kind of a lot. So a second ago, I said that I thought definition 2 is more explanatory than definition 1. And again, my reason for thinking that was because definition 2 does introduce this higher level of mathematical sophistication, but you also might think that the two definitions just aren't comparable because they live in different contexts and they're both kind of equally explanatory when they're in the right context. And so again, that's something that I'm still kind of trying to sort out, is how exactly we compare definitions that are logically equivalent and seem to be giving us very similar information, though the information occurs in different contexts. And so, yeah, so that contradicts what I said a few minutes ago, but I think that you can perhaps think about definition 1 and definition 2 as being both explanatory, but being explanatory in a way that isn't really comparable. So in the sense that both are equally explanatory in their designated contexts. And the last point that I've mentioned before too is that the reception of explanatory definitions isn't going to be uniform. So again, in order to kind of appreciate the explanatoriness of a definition, it's necessary that the person receiving the definition has the right background knowledge to appreciate the epistemic significance and contribution of the definition. So again, whereas someone who specializes in algebraic topology may be very may very well be able to understand and appreciate definition 3. We shouldn't expect that any person kind of in the mathematical realm, in particular students who haven't had any experience in algebraic topology, to appreciate that definition and recognize it as explanatory. And I don't think that this changes the explanatoriness of the definition, but it just, again, I think helps to give us an understanding of progress in mathematics and how mathematics kind of becomes more and more sophisticated. And I think that considering that also kind of helps us to understand why it is that we kind of continually look for new definitions and why presenting a new definition of a already defined concept is a valuable thing. Okay. So I think to sum up here, I think these points about explanatory definitions hopefully illustrate the complexity that explanation can play in mathematics and the role that explanation plays in practice. So in particular, I wanted to highlight that it seems like we get instances of explanations in forms other than just proof. And in particular, when we think about what we want definitions to do for us epistemically, I think we see that they seem to be natural contenders for things that might be explanations. And in fact, I think that they often are explanations. So definitions help to shape our perspective on particular concepts, as well as on areas of mathematics more generally. And so when we have explanatory definitions, we're going to be in a better position for shaping these perspectives and understanding the surrounding area of mathematics. And again, the progression of explanatory definitions and the different degrees of explanatory definitions help us to understand how different mathematical perspectives are related to one another, how mathematics builds off of itself and becomes more sophisticated, and how kind of new perspectives can be gotten from this increased sophistication. And so I think that, again, of explanatory definitions and mathematical sophistication helps us to understand how mathematics is developed and why mathematics is developed in the way that it is. Okay, so in this talk, I had hoped to make a case for the expansion of mathematical explanation beyond talk of explanatory proof to include the consideration of explanatory definitions. But I also want to emphasize that I don't think that mathematical explanation is going to consist of just talk of proof and talk of definition. It's also worth mentioning that though I focus on explanatory definitions here today, and perhaps was critical a bit of the focus on explanatory proof, I don't want to say that explanatory proof isn't valuable. So I think that there are certainly instances of explanatory proof, and that's one form of mathematical explanation, but I think that we need to look to other forms as well. And so I think we need to look at explanatory definitions, but I think that there's also other forms of explanation that exist. So I think a lot of examples can be explanatory, and a lot of diagrams can be explanatory. And so I think in general, we need to kind of be thinking about mathematical explanation more broadly and be thinking about what exactly is the epistemic aim of explanation and how that aim is achieved in mathematical practice in a variety of ways. Okay. And the other point I want to make before I wrap up is, is that to give an account of mathematical explanation that is, I think, complete and is accurately representative of mathematics, I think it's necessary to give careful consideration to mathematical practice and how explanation naturally arises when you're partaking in the practice of mathematics. So I think that talk of explanatory definitions kind of helps to do this because, again, definitions play such an important role in the actual practice of mathematics, both from a pedagogical perspective and from a research perspective. And so I think that when we understand how definitions can be explanatory, we get a better sense of how mathematical explanation is actually arising within mathematical practice. And I think that we do need to give a closer look at the specifics of mathematical practice and how it's carried out and what's epistemically significant in practice to understand mathematical explanation in a complete and accurate way. Okay, and that's all I had for today. So thank you for listening, and I look forward to discussion.